Hello, I'm Rémi Jugier, and I'll be presenting water and ice classification over river and lakes using Sentinel-2 observation with my colleague. So this project is financed by CNES and Magellium. I will be presenting the context and objective, the construction of a training database, and my colleague will be presenting machine learning results and the outlook. So of course, monitoring of the ice cover is important for navigation. It's also important for various climate studies. SAR data can be used to detect ice and water due to the higher ice scatter, but in the presence of waves and wind, the water scatter reaches levels comparable to ice, so it can be confused with ice. Ice scatter can also be considerably lower when it is covered by wet snow. So this is why Sentinel-2 data is useful, because the optical data can be used to discriminate water and ice with more proficiency. However, it is impacted by clouds, which means less availability. So recently, the EA launched a Copernicus service with snow products developed by CESBio and ice products developed by Polska. And Magellium is the main implementer of the service. Polska's RLI perform very well over clear water and thick ice, but they have severe drawbacks when it comes to detecting water over turbid water, over salt lakes, and it also under-detects thin ice. So this is what we aim to improve with machine learning and deep learning methods. So the database was constructed using 29 Sentinel-2 images with detailed labels and using the ALCD classifying iterative process. Of course, we manually correct any issues afterwards. The cloud masks are necessary for ALCD, but we actually use the Maya, which is an atmospheric multi-temporal processor, cloud mask, which are very accurate and which are used to generate the L2 images, which we use for training and test. Here is an example of the classification with the label image on the left and the L1C image on the far right. This is on Gironde estuary in France. We also have a salt lake here in Bolivia, and we also have the Georgia Bay in Canada.
Thank you, Rémi. The machine learning approach used here is the linear SVM fed with all the bands of the L2A Sentinel-2 products of our database, plus some water ice detection indexes like NDVI. And as post-processing, the Maya cloud mask is applied to our product. As usual, our database is split into training and test set, and performances are evaluated on the test set. Here is an example of false detection in existing HRSI algorithms that is corrected with our method, the SVM method, on the Gironde estuary. We can look at the same applies here for the Magellium Bay, where turbid water is classified as ice for the HRSI and is free of ice for our method. The same elimination of false ice detection is applied for salt ice, like here in Uyuni or here in Tazgulu. And at last, the thin ice detection seems to be improved compared to HRSI, as we can see here on the Georgia Bay. But we can see that it still have a place for improvement, like here in Baikal, where a part of the thin ice is detected as water. For quantitative results, we showed here confusion matrices of both methods on ice, turbid water, and salt lakes surfaces only, as these surfaces are the one of interest. As you can see, our method shows overall better performances, even if some improvement need to be made on thin ice detection. As a conclusion, there are considerable improvement of our method for turbid water and salt lakes detection, even if some work has to be made on thin ice detection. Our model should be tested against other machine learning algorithms like random forest or convolutional neural network, which are thought to yield better performances on thin ices due to their spatial correlation layers. Thank you.